Okay, so in our last video, we saw how AI learns from labeled data. Basically, we give the AI an example, and we also give it the correct answer. Dog, dog, cat, cat, bird, bird. Pretty simple, right? But here's where things get interesting. What happens if we take all those answers away? No labels, no teacher, no answer key. Can AI still learn? Surprisingly, yes. Think about this. Imagine giving an AI thousands or even millions of pieces of data. Customer information, images, documents, transactions, shopping behavior. But there's a catch. You don't tell the AI what any of this data means. There are no categories, no correct answers, no teachers saying, this belongs here. So now the AI has to look at the data and figure out if there's something interesting hiding inside it. And this is the basic idea behind unsupervised learning. Instead of learning from data that already has answers, the algorithm works with data that doesn't have predefined labels. It looks for things like similarities, relationships, groups, and patterns. Think about it like this. Imagine I give you a box full of completely mixed objects. Phones, books, cameras, headphones, everything is mixed together. And I simply say, I haven't told you the categories. See if you can discover them yourself. That's basically what unsupervised learning is trying to do. But wait, how can an AI find groups if nobody tells it what the groups are? One important clue is similarity. Think about a table covered with different objects. You might notice that some objects look similar. Phones look like phones. Cameras look like cameras. Books look like books. You don't need someone to tell you that. You can recognize the similarities yourself. Algorithms can also look for relationships like these inside data. And those similarities can become clues for discovering hidden structure. Now let's take that idea one step further. Imagine thousands of data points scattered randomly. Some are very similar. Some are completely different. An algorithm can start organizing the similar points together. And eventually, you might end up with several groups. Group 1, Group 2, Group 3. This process is called clustering. And here's the really interesting part. We never gave the algorithm the groups beforehand. It discovered the grouping from the data. Let's make that even clearer. Imagine thousands of customers. We don't tell the AI which customers are frequent buyers. We don't tell it which customers spend a lot. And we don't tell it which customers buy only occasionally. Instead, the algorithm looks at their behavior. It compares the data. It finds similarities. And eventually, groups start to appear. So the important idea here is the groups are discovered, not given. But now comes another interesting question. What do those groups actually mean? Let's use a real-world example. Imagine an online store has thousands of customers. For every customer, we might know how often they purchase something, how much they spend, what products they look at, and how often they visit the website. Now imagine that none of these customers have a label saying what type of customer they are. The algorithm can look at their behavior and discover groups. Maybe one group buys very frequently, another group buys only occasionally, and another group spends a lot of money. The algorithm discovers the patterns. Then humans can look at those groups and give them meaningful names. That's the important distinction. AI discovers the structure. Humans interpret it. But what if we're not interested in groups? What if we're interested in something that doesn't fit? Imagine you have hundreds of transactions. Most of them are between 500 and 2,000 rupees. And suddenly, one transaction is 48,000. That one transaction immediately stands out. And you might think, wait a second, why is this one so different? This is the basic idea behind anomaly detection. Instead of looking for what is normal, we're looking for what is unusual. That unusual observation is often called an outlier. But here's something important. An outlier doesn't automatically mean something is wrong. Maybe the transaction is completely legitimate. Or maybe it indicates fraud. Maybe it's unusual customer behavior. Or maybe a machine in a factory is starting to fail. So the point isn't simply to say, this is wrong. The point is to say, this is different. Let's investigate. And that's why outlier detection can be so useful. Now let's make things a little more complicated. Real-world data doesn't usually have just 2 or 3 features. A dataset might contain dozens, hundreds, or even thousands of features. And when there are that many dimensions, it becomes really difficult for us to visualize what's happening. Imagine trying to understand a map with hundreds of different directions at the same time. It becomes overwhelming. So how can we simplify that complexity? That's where dimensionality reduction comes in. The basic idea is actually pretty simple. Take complicated data with lots and lots of features and create a simpler representation of it. Think about a huge map. You don't need every tiny detail to understand the main roads and cities. You can simplify the map while keeping the important structure. Dimensionality reduction works with a similar idea. It can help us represent complex data in fewer dimensions. And when the data becomes easier to visualize, hidden patterns can become much easier to see. Okay, so how can an algorithm actually create these groups? One famous approach is called k-means clustering. Let's keep it simple. Imagine 30 people randomly standing inside a room. Now imagine we place 3 temporary centers in the room. Each person moves toward the center that's closest to them. Then the centers move based on where the people ended up. And we repeat the process. Move, adjust, repeat. Eventually, the groups become more stable. That's the basic intuition behind k-means. But there's a catch. How many groups should we actually create? 2, 3, 5, 10? The answer isn't always obvious. And this is one of the important limitations of clustering. An algorithm can find a mathematical structure in the data, but that doesn't automatically mean the structure is meaningful. We still need to evaluate the result. We still need context, and sometimes we still need human judgment. Now let's connect this with our previous episode. In supervised learning, we have data plus labels. We give the model examples, and we tell it the correct answers. Dog is dog. Cat is cat. The model learns from those examples and eventually tries to predict the answer for new data. But with unsupervised learning, we remove those labels. We simply provide the data and ask the algorithm to discover useful patterns. So remember it this way. Supervised learning has a teacher. Unsupervised learning is about discovery. So where can unsupervised learning actually be useful? Well, quite a few places. Businesses can use it to discover different types of customers. Systems can look for unusual transactions or unexpected behavior. Similar documents can be grouped together. Images can be analyzed for similarities. And large datasets can be explored to discover patterns that humans might not notice immediately. The common idea behind all of these applications is simple. Give the algorithm data and let it search for useful structure. But there's something really important to remember. Unsupervised learning isn't magic. Just because an algorithm finds a pattern doesn't mean that pattern is useful. Maybe it creates 5 groups, but only 3 of them actually make sense. Or maybe it finds a pattern that has no practical meaning. So humans still need to ask, is this pattern useful? Does this grouping make sense? And most importantly, what does this pattern actually mean? Finding a pattern is one thing. Understanding the pattern is another. Okay, let's put the whole idea together. Start with raw data. Remove the labels. Look for similarities and relationships. Discover patterns. Create groups. Find unusual observations. And finally, turn those discoveries into useful insights. So if you remember just one mental model from this video, remember this. Raw data, no labels, pattern discovery, structure, insights. That's the core idea behind unsupervised learning. The AI isn't being given the answer. It's searching for what the data can reveal. And now we've reached an even more interesting question. What if AI doesn't have labels, but it does have consequences? What if it takes an action, gets a reward, or receives a penalty, and then learns from what happened? That's a completely different way of learning. And that's what we'll explore in the next episode. Reinforcement learning. No answer key. No predefined labels. Just actions, consequences, and learning. I'll see you in episode 6.